Hello, everyone. Good afternoon or good morning, depending on where you are. Welcome. I'm very glad to welcome all of you again to the new event of the ESO Cosmic Duologues. Hello, everyone. Good afternoon or good morning, depending on where you are. Sorry, there was some feedback, of course. Mistake, sorry, my mistake. As I said, I'm very happy to welcome everyone again to the new event of the ESO Cosmic Duologues. I thank immediately my colleague Henri Boffen and the Office of Science of ESO for the big and the director of science division, director of science of ESO for the big support given for this in this event. Thanks, Henri, for the help, and the people for volunteering and to chairing, and of course our speakers. Thank you very much already since the beginning for accepting our invitation, and we are very glad to have this event today. The topic is the formation and evolution of the solar system. Again, a very, very interesting topic. I just will immediately give the word to Cyril. Cyril she's a fourth-year fellow, ESO fellows. So thank you also for chairing the event. Just the technicalities again. So you are very welcome to send your comments and questions and using the live chat that you have available on YouTube channel. If you are not subscribed to the channel, then you can basically still send your question either via email at ESO2020@ESO.org, or you can use also there is a dedicated form that we have on our pages, duo.eso.org. You log in into the page, you will see a form. You can click on a form, make a question, and there you can make your question. And then basically we are monitoring in real time our emails, so we will able to also give feedback on those questions. We will pass the question to the chair, to Cyril, and she will then use them to basically go on with the duologue. Just to give you again a flavor of the event. This event is, the idea is to have two experts of the field to have a dialogue and to help us to understand and to have a picture inside of some of the basic open question in the field of, in this case, of the formation and evolution of the solar system. And so that's it, I think. Just to give you then, yeah, of course, the video will stay then online, so you can also see the video later on the YouTube channel. Just to give you just a clarification from now on, we have created a dedicated YouTube channel which is called ESO Cosmic Duologue. So you can subscribe to that channel. Sorry for the people who already subscribed to the other channel, but now so there is a more formally is better. So you can subscribe to this channel, and so you will be automatically notified as soon as we start a new event. Talking just very quickly about the next event. Here I have a slide. I hope you can see it. So these are the two further next events that are already scheduled. So we'll have one on Monday 29th and on Monday 6th of July. Again, the next one is on the substructural protoplanetary disk, and then we go high redshift for dusting at high redshift. So still stay with us, and then we are planning another one for maybe for the 26th of July. This is to be finalized, and then we will probably reopen the session in September 2020. So we make a pause for the summertime. So with this, I think I can stop sharing my screen, and I leave the word to Cyril for the event. Thank you very much again, everyone, for being with us, and thank you, Cyril, and the speaker again.
Thank you, Giacomo. First, I want to thank you all for being here today, listening and watching this ESO Cosmic Dialogue. And thank you, Giacomo and Henri for the organization of the events. So this fourth ESO Duologue, as Henri said, is about the formation and evolution of the solar system. And this is a very big question, so the speakers won't be able to talk about everything about this. But this is nonetheless very interesting questions. Because understanding how our solar system formed, how the planets formed, how we ended up with the current structure of the solar system, or water was delivered to Earth. All of those are very big questions that astronomers have been trying to answer for quite some time now, and we still are far from having all the answers. And our vision of how the solar system was formed and how it evolved has changed radically in the past few decades, especially since the discovery of the first exoplanets and the realization that most exoplanetary systems don't look at all like our solar system, and that planetary migration probably played a major role in shaping planetary systems. So we now have sets of models that attempt to match the observational constraints in our solar system, real clues of what happened in our solar system. But we still have some unanswered questions. So I won't say more about this because we have with us two speakers, two great speakers that are gonna tell us much more about the subject. So I'll introduce them to you now. So the first speaker that we're going to hear is Meg Schremm. Meg is a lecturer at the Queen's University in Belfast, and she's working on understanding how the solar system and other planetary systems form and evolve, particularly on the observational point of view. She specializes in using big data for planetary science to study small bodies of the solar system and the surface of Mars, for example. And she's also very involved with citizen science projects and preparing for solar system science with the LSST. And our second speaker today is going to be Sean Raymond from the Laboratoire d'Astrophysique de Bordeaux in France. So he's working on the formation and orbital evolutions of planets in the solar system, as well as exoplanetary systems. And he also keeps a great blog about planets and life-related things that I encourage you to go and look at. It's really nice. So the two speakers are going to give a 20 minutes presentation each. And after that, there will be plenty of time for questions from all of you in the audience. And so, as Giacomo said already, there's a YouTube chat there where you can post your questions directly. Or if you cannot post on the YouTube chat, you can send an email to ESO Duo 2020@eso.org. Or I believe there's also a form on the website that you can use to post your questions. So please go ahead and ask all the questions you have at the end of the presentation. And so with that, I'll leave the floor to Meg for the first of those presentation here.
All right, well, thank you very much for this opportunity to talk about sort of how observations help us sort of constrain the formation, the evolution of the solar system. I think you can all see my screen. So one of the things that I felt was sort of challenging about this talk is in 20 minutes, I can't get through everything I think we know about observationally and what it potentially tells us about the solar system formation. So I'm definitely sort of taking a very fast tour through the solar system with a couple pit stops in different places. But I'm mainly a planetary astronomer studying the Kuiper belt or the Trans-Neptunian region. So a lot of what I'm talking about sort of has that lens or perspective, but there's lots of other evidence from the satellites around the giant planets in the asteroid belts, comets, et cetera, that tell us about planet formation within our solar system. So I can't get to all of it, but I have sort of an outer solar system, maybe slightly more focused for today. But all small bodies tell us really interesting things about the solar system, as well as the planets. And I think why do we want to study solar system small bodies is really because we want to go from sort of that image on the left over to the right of how do we go from forming, from a gas disk, planetesimal disk with gas as it evolves to what we see in our solar system today, because we do know about 4,000 extrasolar planetary systems, or even more these days. But again, the best and closest that we can sample is still our own. And so really understanding the complex dynamics and history that happened here when we can actually go in situ to some of these places and use telescopes to really get up close and personal with these objects, I think, makes the solar system unique and the best, planetary system that we can study. So the small bodies really tell a lot of that story because they are the building blocks, the bricks left over after planet formation. That can tell us what was sort of happening earlier on, where the planets all are dynamic worlds with weather, and like the Earth, have erosion right on Earth or in Mars, and so things are different now than they were back then. So if you want to sort of sample the conditions, you want to go as pristine as possible. And although these objects also have evolved and changed, the smaller bodies maybe can tell us pictures that we can't see from the larger bodies. So I wanted to give a zoom out for most people of what does the solar system sort of look like and how many of these small bodies do we actually have. So this is showing the inner solar system. This is taken from the Minor Planet Center. And so the cyan large circles are, these are the giant planet and terrestrial planet orbits. So we're going out from all the way out from Mercury outward. And so what you're seeing here is all these green dots, red dots, everything pretty much in here are asteroids or some comets coming in. And so really we're seeing mostly these are the asteroid belts. We're seeing the resonant populations that are orbiting Jupiter, as well as sort of all the sea of small planetesimals. And this is just within the asteroid belt. And so again, just every dot is telling you of an object that we know of. If we go out to the, zoom out to the Kuiper belt, and so now we're seeing Jupiter, Uranus, or Jupiter, Saturn, Uranus, and Neptune orbits, right? Now we're seeing what the Kuiper belt is. So again, that whole mass of objects you can't even see for the asteroid belt, right? And so what we're seeing here is what we know about the resonant, like Pluto in the outer solar system in the Kuiper belt. And so again, you're seeing the influx of objects sort of coming in. Again, these are basically short period and long period comets and things we call centaurs, transitioning inward from the outer solar system. But this region sort of out here is mostly dynamically stable in many ways, and we call that the Kuiper belt, with Pluto sort of right here. And again, we know about 4,000 objects that are within this population so far. And so again, by sort of studying all these objects in an ensemble and individually, we're able to probe things about their formation and evolution, or at least that's the goal. And I'm, we're mainly highlighting the small bodies, and I want to make sure at least touch on cometary nuclei and comets, because they are, they're objects that are transitioning in from the outer solar system, either from the Oort cloud or from the Kuiper belt, and that these are telling us, about the interiors of these objects and compositions in ways we can't get necessarily for very small Kuiper belt objects. And various distant small objects. And so this is entire field dedicated to studying the composition and activity of these objects. And each one sort of seems to be, like cats, sort of unique and different, and sometimes behave differently than we think. And so there is a dynamic aspect to studying these objects. These are actively outgassing material. And so it's a combination of studying objects that are active and more quiescent, that we get a good understanding of what these objects are made of and how their evolution sort of impacts their overall history of what their parent population might have looked like. So whenever we talk about solar system objects or small bodies, I like to sort of at least show one slide representing how do we actually find these. And it's not so hard generally, but it is really looking for the things that move across the sky. And we normally do this at opposition, so that we're looking sort of perpendicular to the Earth's motion, because covered objects are only moving about 3 kilometers per second compared to the Earth's 30 kilometers per second. And so you can use the Earth's motion to basically effectively give you parallax to see these objects moving across the sky if you're looking at opposition, so directly perpendicular to the Earth's motion. And so here you're seeing a frame, I believe this is of Eris, and sort of can see the moving dot, but also you might notice there's a dot that appears and goes away that's actually an asteroid. So again, simply by just the motion of these objects, we can sort of differentiate roughly where they are and within the solar system. And then with further observations, we can also get much better detail of their orbit properties, as well as, right, just from the brightness of these objects, get an estimate for potentially their size, but at least we have a brightness distribution from measuring this and many other objects. So effectively, telescopes have been sort of surveying the sky, looking for these objects. And I think, with the CCD revolution, we've really seen wide field cameras take off more and more and more to enable being able to find these objects. So, it's good to talk about them as points of light, but I also wanted to sort of zoom out a little bit and talk that there are objects that effectively whirl. These are the end points, the end stages of those construction zones, right, of planet formation, but that also these are building up to potential planets. And so really, both the asteroid belt and the Kuiper belt are sort of at that last oligarchic stage before you sort of form the things that form planets. And so Pluto didn't quite get to the point to go any further, but it does tell us something unique about planet formation that some of these smaller objects that are maybe 100 kilometers that reside in the Kuiper belt can't tell us. And so again, this is a new horizon image, but Pluto has weather, it has seasons. There's a lot of potentially, a lot of geology and active processes that have gone on in Pluto. So just to highlight that, although a lot of times we talk about these objects on this sort of ensemble, especially for the smallest ones, the largest also tell us something unique because they're at a slightly different stage of planet formation. And so again, they're kind of all worlds, especially in the large size. And again, to highlight that, there are ice mountains that we've seen from New Horizons data. So again, mission data gives you a perspective that we necessarily can't get for the ground. It also tells about things about the largest ones that don't happen on the smallest ones. So there's this interesting balance between how you study the different objects in the population. And again, if we're starting to go to smaller objects, so Pluto is about almost 1,200 kilometers in size. We're going down to Arrokoth, which is about 35 kilometers long. And this is a cold classical Kuiper belt object. It's a small object and part of the Kuiper belt what we think formed in situ. And so this looks like it's really sampling planet formation as it happened in that region around 30 AU, 30, 40 AU. And so we are seeing this object with having these New Horizon images. I think we're going to see over the next years and decade so much studying of these images to understand how this object might have been put together just from having a spacecraft fly by, because we can't see this resolution from the ground, and hopefully be able to interpret what we can see here from what we do get from the ground to apply this to more objects. And I don't want to leave the asteroid belt out in any sense, but this, just to show this is Ceres. So again, there are dwarf planets or that large end state before, at the end of oligarchic growth, sort of before we get into maybe things that are more like planetary cores. Here, so they do exist in the asteroid belt. And same thing, there's small rubble piles also existing in the asteroid belt as well, like Itokawa. So Ceres is about 473 kilometers in radius, and Itokawa is about 330 meters all the way across. So again, both these populations have large and small objects, but still relatively small compared to what we deem planets. And again, I just want to highlight within the Kuiper belt, there are already about 10, 12 objects that are similar size to Pluto. And so they really do represent a subset and a unique set within the Kuiper belt. These are worlds compared to maybe small rubble piles or obelisks. And so they do sort of differentiate out as being different. And I think that's something that's come over the past decade or so of really understanding how these objects differ from the rest of the population, and what these objects as sort of lighthouses, as the brightest objects, the ones that you can get pretty good spectroscopy on, can tell us. And one thing I want to highlight, just sort of going in this whirlwind tour, is it's been with the advent of wide field cameras and CCD technology that really ability to really detect large numbers of Kuiper belt objects has come up. These objects are faint. 21st magnitude for us is considered bright. Most of these objects are much fainter than that. But also getting around observing biases, where you point in the sky and what objects you detected and recovered to get very accurate orbits matters when you're trying to get into population statistics. So I wanted to highlight one survey that's done an excellent job for the outer solar system, and that's the Outer Solar System Origin Survey, which has detected over 800 Kuiper belt objects using the Canada, France, Hawaii telescope and the MegaCam wide field instrument. And so this survey has the ability for us as planetary astronomers to take this data set and the number of objects they detected and what orbits, and understand what was detected and why, and what also wasn't detected, which is more important. So to be able to test these formation models, both in terms of orbits and properties, because we know what would have been found in the survey, and there's a survey simulator because we know all the biases and what was detection efficiencies to be able to put through any model that we can think of for the solar system. And so I think it's really important that that's been progressing over time, and also this is just one survey that sort of culminates that with a large sample that does this on a very large sample in very large area. But this has sort of been culminating, I think, over the last 2 decades. Another way we study these objects is, brightnesses and orbits, but also in composition, reflectance spectra, and broadband colors. So for the very brightest objects, we can actually get optical near and infrared spectra. So on the right, I'm showing these are the dwarf planets and their reflectance spectra. So they have methane and ethane and nitrogen and CO ices on their surface that are detectable. Unlike this, then the smaller objects tend to have very flat spectra. In most cases, we can't get good spectra, reflectance spectra. So we're actually getting optical colors or near infrared colors as a proxy. And this is just an example of showing photometry points and maybe some of the optical bands where they sample it, and where you might be able to tell differences within the object. And mostly we see for these objects, and I can show you here, were ones that the community has been able to get spectra on the smaller side. most of these are pretty flat spectra. And so again, this photometry where we can do sample a few points can tell us that optical or near infrared slope, which we can use to sort of understand these objects and potentially look at composition and how the composition in the primordial disk was, if we can understand how each one of these objects was placed into its current orbit today. And so just to highlight that the two stars here are just showing you more the dwarf planet candidates, large objects in the Kuiper belt that sort of behave differently and have volatiles on their surface. And you can see that most of the other ones are pretty flat. And so again, right, we've really found that most small Kuiper objects have pretty featureless spectra, and that they're in a regime where it takes a lot of time and energy to get spectra of these objects, but we can use Brabant colors as a proxy, which has sort of, I think, been in the last several years a very big push in the community. And I don't want to, just talk about composition. There's other ways we can sort of get an idea of shape. And again, you can use a rotational light curve where you're looking at things that are due to shape or albedo, or if it's contact binary, these all can show up potentially in that light curve that we see. And though there's some degeneracy, we can use that rotational light curve or that brightness over time changes to get some sense about the overall properties of these objects. What are these shapes telling us potentially, or the angular momentum distribution within the Kuiper belt and how that might have evolved over time. And this is just an example of showing it's not all easy to do. That again, this is data from the same object, and it looks like a single peak light curve and a double peak light curve fit the observations both pretty well. And so that there is, a lot of observations that go into this and still some degeneracy even when trying to find out these parameters. Another interesting way to tackle these objects is, again, we're looking for moons. If we can get moons, we even can identify that there is a secondary object, it means we can get mass. And if we have some estimate of size, either from its brightness or again, combining optical and thermal observations, then we can do more and get a density. So these are just two of the dwarf planets. Almost all the dwarf planets pretty much have satellites, which makes them more distinct than the smaller objects, which don't have, we do see binaries, but we don't see them at the rate that the dwarf planets do. So there is something different about how these satellites are formed compared to ones we see for smaller Kuiper belt objects. And this is just to show you the densities of the probable composition. That we can see that this is just showing bulk compositions that are measured for a series of binaries within the Kuiper belt. And that again, we're just sort of seeing that the largest objects are more dense, and then also seeing some trend up here with diameter. And we don't fully understand, I think, all the reasons why for this, but the beauty is that having this data means we can start exploring things about bulk composition and structure as we get more objects that are binary and get more of these measurements, and particularly showing that the dwarf planets, again, stand out. So you have to be careful when you want to compare the population about which objects you choose and especially what you're looking for. And just again, the ensemble properties, I think, of the Kuiper belt and of the asteroid belt tell us a lot. And I think that's a lot of where our work is both in sort of understanding the bulk, but also the devil in the details of what each one of these things can potentially tell us about the composition of the original planetesimal disk and the history within the solar system. And I just want to highlight briefly that there's a lot of structure within the Kuiper belt that I could give an hour-long talk just on that. And so here I'm showing semi-major axis versus eccentricity. There's Pluto sitting at, Neptune sitting at 30 AU, so our lovely ice giants. And basically you're seeing that the two lines are showing you perihelion at 30 and 48 AU. And the main point I like to point out in these diagrams is that you see there's a population of low eccentricity objects sitting here at around 40 to 50 AU, and that we call this the classical belt. And that Plutinos, we see that these fingers, they're actually resonant fingers. So these are objects that are in V motion resonance with Neptune. So Pluto's in the 3 to 2 resonance. It resides here with the rest of the objects nicknamed Plutinos. And they're orbiting twice every time that Neptune goes around 3 times. And this is a saving resonance in the fact that it actually protects objects that are crossing over Neptune's orbit and protects them actually from being scattered and moved out of their orbit by Neptune. And then you see here, there's objects with large semi-major axes and eccentricities, and these are what we call the scattered disk. And so already just by getting surveys that find these, right, we've already been able to say there's a lot of structure here. And you can ask, how did all of that form? And we know from this that, there clearly has to be something that stirred this disk, because if you just had a planetesimal disk with gas anything that scatters objects should bring it back to circular orbits. So the fact that you have a whole population that is not on circular orbits, things that are in pretty highly inclined orbits and a mean motion resonance, is telling you something has happened and something's perturbed this population after the gas has gone away. And same thing, if you look at inclination, you see that there's the cold classical sitting down here, my mean motion resonance fingers, but there's also a lot of high inclination objects and ones that have high eccentricity as well as semi-major axis. And so all these objects, except for the cold classicals, are sort of dubbed the dynamically hot population within the Kuiper belt. And so probing their properties compared to cold classicals has had really, I think, sort of revolutionized or sort of picture at least of what's going on in this region and what it means for what happened earlier on. And a lot of what it said is that the giant planets have moved stuff around, scattering planetesimals. And originally it was that the cold population, these cold classicals were in place or maybe moved out altogether, with the hot population coming from being scattered mainly by Neptune and emplaced into the Kuiper belt today, which means that the hot population is telling us about things that are what happened beyond or closer in than 40 AU, where the cold classicals are telling us about what happened at 40 AU. And it also means in this whole scenario is that Jupiter moved inward and everybody else moved outward. So this is a nice simulation showing that. This is the NICE model sort of migration is typically the way we call it simulation, but it's a group of people that have really looked into doing this, and that the idea being that Jupiter and Saturn interact in a mean motion resonance and causes chaos where we see the entire, the giant planet sort of reorganize based on that. Let's see if it goes. There we go. So here's really a quick summary of that, just showing you that in a slower scale. And again, here's another way of looking at it in terms of semi-major axes, eccentricity, and perihelion over time. And we really see that Uranus and Neptune actually switch positions, and that when this mean motion, Jupiter and Saturn go eccentric, it causes Neptune and Uranus to also behave this way. And again, this is planetesimal scattered migration that is occurring and things are being scattered. And so with this model, you get something like this, where the NICE model can produce things that look like we see in the Kuiper belt. You see it produces these resonances, but it doesn't necessarily produce those cold classicals. And there have been attempts to tweak this that have been able to do that, or at least reproduce it somewhat, but not exactly. So on the left, this is again the model, and they can kind of produce some cold classicals, but it doesn't have quite the right eccentricity distribution to match the data. And so we know from colors that cold classical objects differ in color from the rest of the Kuiper belt. So here's just showing optical versus near G minus R versus R minus J. And so you see that most of the cold classicals lie much redder than the hot population, which has a blue component, but also objects that are redder. And by blue and red, I mean really everything's redder than the sun, but it's red and more red. So we call it blue if it's closer to the sun and red if it's further away. And so we know that the cold classicals have binary distribution that's different, size distribution that's different, color distribution that's different. So how do you then form it in this way with a NICE model? The NICE model sort of argued that they would have looked like the hot population if you could, if you really, they produced in this model where they were part of these mean motion resonances that leaked objects in. And so, knowing all this observational data, I think we've learned more about what's going on, and that we see here. These are wide binaries. And so what the interesting thing about them has been is that these objects would be completely ripped away if they had been migrated with Neptune. And these are sitting in the cold classical belt. And so we know that if these objects are sitting there, there's no way that these objects could have migrated and been interactive with Neptune. So that plus all the information we've had about the cold classicals, that they're different, really tells us that although some versions of the NICE model can make a cold classical belt somewhat, they're actually not formed there. They came and they really were formed in place and are not from some population being scattered in, and that they're primordial. I think that's been a shift over the 10 years that we've seen, that again, the sort of original model for NICE that doesn't have those tweaks is a much better fit to what we're seeing. And again, just showing you the last migration models, this is actually the latest to date with the jumping Neptune, where it actually jumps a little bit, really does produce what we see for the hot population, assuming the cold classicals formed in place. And again, we can do a lot of things to understand how these objects formed, doing details about how and what we can learn about composition from these, about where we might see objects like that. And so we're doing surveys, again, doing these kind of color surveys with smaller objects, potentially be able to figure out those fine details of how Neptune migrated and where those color distributions might be. And this is just an example where now we found a way with the Z filter that for Kuiper belt objects, you can actually identify co-classical surfaces where they drop out. So in G minus R versus R minus Z space, the co-classicals reside here and break away from the rest of the hot population. Unlike here, where you see there's combination of red hot population objects and co-classicals. And here, if you see when we get that R minus Z and G minus R, they clearly go away on their own. And so this is going to be a unique probe, I think, moving onward that will be able to detect these. And so I just want to highlight, just to ending and say that there's a lot you can talk about, and the asteroid belt has had its own migration, and just say that the Grand TAC is a potential model where we see in composition differences in the asteroid belt might be produced by actually having having Jupiter and Saturn migrate inward and then migrate outward, causing a distribution of compositions that look similar to what we see in the asteroid belt. So lots of things we see in the asteroid belt can tell us a lot about the history that we don't see necessarily in the Kuiper belt. And so I'll just say that there's a lot of things that can be done. There's a lot we can understand about understanding the potential for Planet 9, but there's no time to talk about that. But I'll just say that a new survey is coming online in 2022 called the LSST. So the Rubin Observatory and its legacy survey of space and time, and it's going to detect over 40,000 Kuiper belt objects, 5 million asteroids. And so all the things that we're doing now, we're going to be able to bulk up by a factor of 10 or more. And I think we're going to be able to get answer some really interesting fine details about this story we've been able to tell about the solar system, both for the asteroid belt and the Kuiper belt. And so with that, I've got further reading if people have, want to learn more about this, both for dynamical evolution and the Kuiper belt. So I'll leave it there.
Thanks a lot, Meg. That's a great presentation. So I think we can move to Shen's presentation now. I'll leave the questions for after.
Okay, so I'll just go right away. All right, so share screen. All right, so you can see that okay? See my slides all right? Okay, yeah. Cool. So it's a pleasure to be here. And so I'll kind of pick up where Meg left off and talk about the theoretical framework of solar system formation and kind of current thinking about the key steps in what shaped the structure of the solar system. So I should introduce myself. I'm Sean Raymond. I'm in Bordeaux. That's my blog, Planet. And I'll just acknowledge some of the people that I've worked with over the last several years that have shaped a lot of my thinking about this. And so many of the ideas that I'll present are kind of, I want to give them some credit as well. So moving along, you can think of solar system formation as kind of a puzzle. And so you can get a puzzle of the solar system on Amazon. There's a bunch of them. And so I like to think of, understanding the formation of the solar system as being like a puzzle where we want to put together these pieces to build solar system. But what are the pieces? The pieces themselves are kind of processes of planet formation. And so if we really want to get a big picture view of how the solar system was assembled, well, we can't do that if we don't have pieces that make sense. So a lot of planet formation work is done on understanding individual, processes, things like, structure and evolution of disks, pebble accretion, migration, all these kind of processes. And then the goal is to take those kind of, processes and put them together and see if they can fit together to tell a story that can reproduce the solar system. So that's the kind of goal. And so in this talk, I'm going to just kind of present briefly the general ideas we got in sort of a cartoon-like view to just give you the main ideas. And if people have questions on details, we can talk about that afterwards. So the general setting, of course, is the sun and its gas-dominated disk, right? And so within the disk, little grains of dust start to grow and collide, and then they start to decouple from the gas. And so once that happens, grains of dust can drift, and drifting dust is often called pebbles. Dust generally is thought as the dust that gets swept along with the gas, and once particles get big enough to decouple and drift through the gas, they're often called pebbles. So here kind of pebbles have drifted and clumped together. And in this animation, you can see they keep clumping, and there's an instability called the streaming instability that's triggered here that can cause particles to basically clump together and go directly from, say, millimeter, centimeter sized pebbles up to, you know, planetesimals, things we think of as being 100-kilometer scale objects. These are the kind of the first macroscopic solids in the solar system. These are what we often think of as the building blocks of planets. And the leftovers that don't end up in the planets are things that we can see in like the asteroid belt and in the outer solar system. All right, and so the next stage of planet growth involves planetesimals bashing into each other to grow further. And also they can keep growing by grabbing onto pebbles that are drifting in the disk. So remember, pebbles are just dust that gets big enough to decouple from the gas. It feels a strong headwind from the gas and drifts inward. And so a planetesimal on an orbit that's mostly fixed will see kind of this flux of pebbles drifting inward. And what's interesting has been and really been explored in the last decade or so is that pebble accretion onto large objects can be really efficient. So this animation sort of demonstrates that. So a large planetesimal in the center there is shown. And so another planetesimal goes by that only really feels gravity, and its orbit is deflected by the gravity of the large body. But the small pebble, because of gas drag, can spiral in there and accrete. And the accretion rates from pebbles can end up being very high. And so it's a very powerful mechanism that now seems to be kind of a key piece in the story of how planetary systems form. So back to our cartoon picture. So within a disk of gas, once planetesimals form, those that form kind of close to the sun where it's hot enough will be mostly rocky. Further on, you know, past the snow line, you can imagine these things have a component of ice as well. And then, you know, as these objects continue to grow by grabbing onto pebbles that are continually drifting inward, what's interesting is that past the snow line, we think the pebbles are bigger, you know, maybe centimeter scale, whereas they're more like millimeter size inside the snow line. And that causes a big difference in the efficiency of pebble accretion, such that the growth of the next phase of objects, things we call planetary embryos or cores, is much, you know, is very affected by where objects are. And so objects past the snow line, you know, will grow to several Earth masses. And in that time, in the inner solar system, planetary embryos are only about the mass of Mars or so. And this is just because, at least we think, this is because pebble accretion is much more efficient past the snow line because of this size dependence. And this is nice. This is kind of conceptually sort of looks broadly like the orbital structure of the solar system, although it doesn't always have to be that way. So from here, let's take a little small tangent towards meteorite land. So this plot shows the age distributions of two general classes of meteorites. So a very cool development in the last 10 years or so in meteorites is that rather than having many, many different classes, subclasses, because of isotope analyses, you can group them into basically two groups. And these are called carbonaceous and non-carbonaceous groups. And here they're shown in blue and in red. And basically all of the, you know, these ones that formed very shortly after time zero when CAIs formed, these are kind of iron meteorites and such. Past a couple million years, these objects out here, a lot of them are chondritic meteorites. They're chondrites. And so their parent bodies are inferred to have formed 2, 3, 4 million years after CAIs. So what's interesting about this and the connection with pebble accretion is that chondritic meteorites contain chondrules. Those are basically pebbles. They're little small pieces within meteorites that should drift really, really fast through the gas disk. And so carbonaceous and non-carbonaceous meteorites, they have different isotopic anomalies. They look different. They're different enough that we think that they formed in different places. They represent different reservoirs within the disk that were spatially separate, yet they were forming at the same time. So what does this mean? We think that this means that something was keeping them apart. So some mechanism within the disk or with planets forming kept them apart. And so what could that be? Well, the first idea that was proposed was that, you know, kind of within this framework where planetesimals are growing into planetary embryos by grabbing onto pebbles that are drifting. Well, when one planetary embryo gets big enough, it actually generates a pressure bump in the disk exterior to its orbit that traps pebbles and shuts off the flux of pebbles. And so imagine that this guy right here grows big enough, and say that, you can imagine maybe that's Jupiter's core. Once it reaches a critical mass of about 20 Earth masses, depending on the details of the disk, it blocks the flux of pebbles into the inner solar system. And so what's cool about that is that would divide the inner and outer solar system. The chondrules in the inner solar system would be different than the ones further out. At least they would be kept, if there are two reservoirs, they'd be kept separate. And so this is kind of a neat idea. This would be a connection between meteorites and what's going on, how our solar system actually formed. The story is not quite so simple because there's more than one mechanism that could potentially explain this. So on the left here, what you're seeing is kind of another kind of conceptual picture of Jupiter's growing core dividing the solar system in two. But another idea out there is that it's not Jupiter's core growing that caused this, but just a pressure bump within the disk. And there's many different mechanisms that can generate pressure bumps. And so it's possible that the fact that there's two different classes of meteorites with overlapping ages is telling us more about what was going on in the disk rather than the growth of the planets. So that's an open question, exactly what it means, but it's really important, and it's definitely connected to what was happening. So now let's talk just for a moment about the growth of the giant planets. So if we just throw two ingredients in the mix, which is pebble accretion, right? Grabbing onto objects, these dust that's drifting inward, grabbing onto the pebbles that are drifting inward, as well as orbital migration. So that's the orbits of planets being torqued by the disk and generally going inward. Then we can look at very simple growth and migration tracks for planets. And so what this plot shows is with just those two ingredients, the mass versus orbital separation, each of these lines is just showing the kind of growth track of one planet growing by itself, just to illustrate the different ideas. And so what you can see is, imagine kind of the seed of a planet started at about 5 AU. Well, it kind of keeps growing. It grows pretty quickly. Then it starts to grab onto some gas from the disk, and it migrates inward and ends up as a hot Jupiter. And what happens in these kinds of simple models, it's really hard to end up with planets that look like Jupiter, because anything that starts inside about 10 AU ends up as a hot Jupiter right close to the star, rather than something that looks like our Jupiter. And so, you might want to know, and I think we want to know, why does Jupiter at 5 AU instead of being a hot Jupiter? Right? Obviously, that's very important for us in the solar system. And we don't know. I'll throw out a few ideas right now. Maybe Jupiter's core itself did form out there at 15 or 20 AU, so it did migrate inward quite a bit to end up at 5 AU. Maybe the disks are very, very low viscosity, at least in the midplane, and so migration is much slower than assumed in those kind of models. Maybe the disk, it was evaporating from the inside out fast enough that, as you can kind of see, this is just showing kind of evolutionary stages from the top down of a cartoon disk that's photo evaporated by this UV light from the central star from the inside out. And so if a planet is migrating inward, and it can run into this edge and get stranded. So photoevaporation can trap planets as well. Or finally, maybe it's something to do with Saturn, and Jupiter and Saturn together don't necessarily migrate inward. And we'll talk more about that in a second. So now let's look at the inner solar system. So I've been involved a lot in models for trying to reproduce, especially the inner solar system. And so what exactly does it mean to try to reproduce the inner solar system? Well, this is the cartoon inner solar system that I like to show. So what exactly are we trying to match here? Well, we have about 2 Earth masses in rocky planets. Then there's this big gap, the asteroid belt, that only add up all the asteroids, they only make less than 1,000th of an Earth mass. And then past there's the giant planets that had to have many Earth masses in solids, and presumably to build their cores. Now, in the asteroid belt itself, there's not a lot of mass, but there's still a lot of orbital and compositional structure. And so when we try to reproduce it, we want to match some details, but we can't ever hope to match every little wiggle. And so there's some compromise going on there. The kind of key quantities that are trying to be matched by models are things like the numbers and masses of planets, their orbits, how fast they grew, and the general structure of the asteroid belt. So that's kind of the target. Now, there's models that have been trying to do this for a long time. what we call the classical model was developed by George Wetherill, and many others. And people have been modeling this for decades. And the general assumption of the classical model is that we can treat the formation of the rocky planets separately from the formation of the giant planets. And so there's good evidence that the rocky planets took longer, or at least Earth took 50 or 100 million years to finish its growth, whereas Jupiter had to grow during the gaseous disk phase, which only lasted a few million years. So let's just kind of assume that we can treat them separately. That's the general assumption. And I'm going to summarize many years of work on this with one little cartoon. And so starting from this type of initial condition where there's a disk with some gas that dissipates and a bunch of rocky stuff that bashes together and grows things, what happens in simulations of the classical model is something like this, right? So this is the solar system that emerges. So we do pretty well at matching things like Venus and Earth, but not so great with the rest. So you can see Mars, we form planets at about Mars's orbital distance, but they're usually way too big. They're usually about the size of Earth. And the asteroid belt doesn't usually look good. It usually looks overpopulated. It often has Marses stranded in there, which is not good. And I don't even want to talk about Mercury because Mercury is a whole other problem. But we can kind of boil this down to a couple key problems. One of them being the Mars problem, the small Mars problem, which is pointed out first in the early 90s by George Wetherill. Right? It's hard to reproduce the large Earth to Mars mass ratio. The two planets are right next to each other, but Earth is 9 times more massive. That's not what we get in these kinds of simulations. And the second problem is that the asteroid belt has too much stuff left over, and the orbits also are bad. Okay? So these are problems. And right now there's a few different possible solutions. So there's 3 of them, and I'll go through them one at a time, just in very simple form to give you an idea for what we think may have happened. So each of these solutions is kind of its own idea. And we don't know which one happened, if any of them, but each of them is kind of on a similar level in terms of being able to reproduce the inner solar system. So we'll start off with the first one, the low mass asteroid belt model. So the assumption here is that the solution to this problem relies on how planetesimals form. And so as we talked about, the asteroid belt is mostly empty. And so the assumption made in this model is that it was always that way. Almost no planetesimals ever form there, right? Maybe a few, but not a lot, okay? And so, you might ask yourself, why would this ever happen? This seems very strange. Well, you can justify it by thinking about observations of disks around young stars. They often show ring structure. And so you can imagine that the streaming instability is very sensitive to the local gas to dust ratio. Well, those clumps like there where there's a lot of dust, a little bit more dust, well, maybe planetesimals are forming there. But in the little rings next door that have a little bit too little dust, the streaming instability is not happening. And some models do find that under certain assumptions anyway, rings of planetesimals can form within disks where dust is drifting around and forming planetesimals by this type of streaming instability. So maybe it's possible. So assuming that it's possible and that rings of rocky planetesimals really can form, then let's see where that goes. So what we have here is, imagine there's a ring of rocky stuff containing a couple Earth masses, a mostly empty asteroid belt, and then some stuff further out to form the cores of the giant planets. Well, from that, again in cartoon mode, the terrestrial planets form naturally. Earth is naturally big, Venus is naturally big because they formed within this ring. And Mars is small because it was kicked out. And just based on that very simple initial condition, you can reproduce the structure of the terrestrial planets really well. You might wonder about the asteroid belt. Does that still work? And imagine if the asteroid belt started off empty, it's not completely empty now. And it turns out that the growth of planets, interior and exterior to the asteroid belt, naturally dumps some leftovers in there anyway. So it's not so hard. So the growth of the giant planets naturally dumps some material in from the outside. The growth of the rocky planets naturally dumps some stuff in from the inside. And basically, the asteroid belt now contains stuff from the whole solar system, not evenly sampled, but basically stuff from all across the solar system was implanted into the belt. So you end up with a belt that looks about right, even if it started off mostly empty. All right, solution number 2 to these problems depends on the migration of Jupiter and Saturn. So this is migration within the gaseous disk. And this image is showing a snapshot from a hydrodynamical simulation of Jupiter and Saturn that are circled here, orbiting within a gaseous disk that's intended to represent the sun's planet-forming disk. And so you can see they've mostly cleared out this gap of, so there's very little gas here in between this inner part that's denser and the outer part that's less dense. And the torques acting on these planets can cause their orbits to shrink or grow. And the general evolution that's seen, at least for a subset of conditions, looks like this. And this is the foundation of what's called the Grand Tack model. So the very simple idea is that left by itself, Jupiter would kind of grow a little bit, start migrating inward and keep going inward forever. But Saturn doing the same thing and catching up to Jupiter can cause them to both go outward together. So the two planets, when they're close enough together and the outer one is less massive, can actually migrate outward. And that's sustainable for a long time under certain conditions, conditions related to the planets and the disk. And so going with that as the framework for how the planets may have migrated, we can see the effect that has on the rocky stuff. And so again, in cartoon mode, because I made all sorts of cartoons here. So starting from this distribution of rocky material, if Jupiter migrated inward and Saturn came and caught up and they both took off outward, what happened there is that a smooth kind of broad disk of material ends up being squished into a ring. And from that point on, we had the same conditions as the other model. And so it makes sense that the planets that form have about the right orbital structure. And the Grand Tack can also match the asteroid belt as well. And finally, the third model is built on the idea of the instability in the solar system. And so Meg already talked about this a bit. It's often called the Nice model, at least it was in its first version. Now it has different names here and there. And so the details of this instability have been revised in time. And now basically it's continually revised to be as consistent as possible with thinking of what should have been happening earlier and ideally consistent with what we see in the solar system. In the end, this instability can reproduce a lot of small body populations within the solar system, as well as the orbits of the giant planets. So we think that it really happened. And as you can see in this, this animation, the general idea is that the giant planets would have formed on more compact orbits, probably in resonances, with an outer belt of leftover junk, right? Leftover planetesimals that never made it into planets. And something triggered an instability and cleared out most of the outer stuff and brought the planets to their final orbits. And one of the planets was probably even ejected in the instability, an extra ice giant. So what's different, why this is kind of still a current idea, or at least one aspect of that, is the timing. This model was initially developed to explain the late heavy bombardment, but evidence for that has kind of disappeared. And so the initial kind of part of what was very ad hoc in the initial version of the model was that the instability had to wait for several 100 million years. And now that's not the case anymore. And so the instability still seems like it happened because it can reproduce a lot of different aspects of the solar system. But it probably happened early. So what's new is that this probably happened early, at least within the first 100 million years after time zero, probably much sooner than that. So then you might ask, well, could that have affected the formation of the rocky planets? And I'm glad you asked, because I have a slide on that right now. And so the answer is, of course. So if the instability happened during the growth of the rocky planets, it would strongly affect them. And so how would it affect them? Again, in cartoon mode. So that's Jupiter going unstable there. It's not here, I'll show you that again. That wiggling is the instability, boom. And so what I'm trying to depict very quickly in this cartoon is that the instability and kind of the orbital excitation caused by it really strongly affects the asteroid belt and kind of goes inward to Mars's feeding zone, but not so much to Earth. And so it affected the growth of Mars, but not so much of Earth. And so it can naturally match the fact that Earth is much more massive than Mars. And it can reproduce the asteroid belt as well. So it's on similar footing to the low mass asteroid belt and Grand Tack model. And it's called the early instability model. So we have these three different possible solutions to explain the structure of the inner solar system, but each has a potential Achilles heel. So the low mass asteroid belt's possible problem is really the initial conditions. Does it really make sense for these rings of planetesimals to form right next to a mostly empty asteroid belt? For the Grand Tack, it's actually the migration mechanism, right? The outward migration mechanism works great if Jupiter and Saturn have a certain mass ratio, but they really should be growing as they're migrating because they eat gas at the same time as the gas drives their migration. So can they maintain that ratio as they migrate? And for the early instability model, the key is the timing, the true timing. And this one is the most clearly testable with kind of cosmochemical studies in the future, I think. Because if we had a date of when it actually happened, we could say, well, that was too late to affect terrestrial planet formation, or it was early enough that it must have. And so going back to kind of the puzzle that I showed you at the beginning, so based on these pieces of the puzzle, you know, which ones are the most important? Well, I can't just say one or two, at least a few, you know, hopefully I've shown you that there's a few pieces that are definitely really important. Things like pebble accretion that we can compare to meteorites. Things like the dynamical instability, like giant impacts that I didn't actually talk about, but they're important. And then there's other things that we want to know more about, like the structure of the sun's planet-forming disk. We don't know that much about it. Details of migration, details of gas accretion, where and when planetesimals form. These are things that are definitely really important that we don't know a ton about, and we would like to know more. And so I'll stop there. If you want more information, a lot of this, you can get it from a review paper that came out a couple of years ago. I think it's officially published around now in a book. Or Alessandro Morbidelli and I made a series of videos on YouTube called the Mojo videos that are kind of funny if you're interested. All right, I'll stop there.
Thanks a lot, Chen. It was really great. So I think we're starting to see some questions in the chat. So please, anybody with a question?
I'll stop sharing, right? Yeah.
Yeah. Oh yeah, it stopped sharing. So everybody who has a questions, just please go ahead and ask them in the chat. I'll just come to it and read it later. And so I'd first like to start and asking the two speakers, Sean and Meg, if they have any questions for each other, you might want to ask.
I got a question for Meg that I've been wanting to ask for a while. So what's up with LSST is going to find so much cool stuff. Why only like 10 interstellar objects?
That's actually better than we thought it was. So we don't know. So interstellar. So that's a question mark. So we know that, like, you know, we had one interstellar object, which is Oumuamua, and then we have an interstellar comet. So the second object, Borisov. But we're again modeling these on a thing where we don't really know the dynamics very well, right? So we're using modelers who give us one population of orbits and trying to make an estimate. So the lower bound is probably, it was 1 a year based on Oumuamua, and then with 2, it's like, well, let's be a few a year. So minimum's like 10, but it could be a lot more. We just don't know. So that's one of the cool things is that we'll be able to find out, because we'll be able to actually put a number on that. And one of the hard parts right now is that, again, surveys are doing this, but it's not clear we know the biases of finding these objects. And a lot goes into confirming, right, their eccentricity has to be greater than 1. They need to be on hyperbolic orbits. Are there biases to finding them that maybe are there, or keeping up to actually see the orbits beyond that? So the nice thing is LSST has a data set that's will be widely available, where we know where it pointed and how deep it went and how good the algorithms are for detecting these types of orbits to be able to actually put a really good number on it. So yeah, it's one of those open questions that we went from like there being none to, okay, now we know there's 2 to how many is it per year? So it's gotten more optimistic. It was like, maybe we'll see 10. And now I think it'll be a few a year, which will be exciting, because the cool thing is we talk about everything about the solar system. These come from somewhere else. These are objects from some other planetary system that formed about, that came in, right? Or like, you know, got ejected from their solar system and sitting around in interstellar space, wandering around, maybe interacting with other stars, and then come in, and they're only here for a short amount of time. That tells us, can tell us about sampling planet formation and testing your theories around other stars. And already we see Borisov is pretty vanilla. looks like a lot of what we see, but or rather Oumuamua is very vanilla. It looks like what we see, but Borisov's kind of like pistachio. Like it sort of exists, but it's weird. It's not a flavor that's maybe appears very often when they're in a solar system. I think there's one object that has one comet that's been measured that has a C to O ratio that's higher. And so it's a pretty non-usual solar system object if you didn't know it was interstellar. And so it clearly has a different composition than our solar system on average for most comets. So yeah, it's going to be exciting both on the numbers and also just on compositions.
Yeah, totally. I guess you'll have a much longer, even if the detection rate wasn't that much higher than for what we can do now with pan-stars and stuff, I guess you'd have a much longer observing window anyway, as well, I would think, being able to go much deeper.
Maybe.
Or I
So
guess
altitude is going about 24th magnitude. So we'll see. It'll be interesting to see how much more it can get. But even with that sort of estimate is a few a year is right now the optimistic estimate. And Sean, I wanted to ask you, I know this question comes up a lot, right? When we compare to extrasolar planet systems, there's a lot of super Earths. And super Earths, mini Neptunes. And our solar system didn't seem to have that. Although, maybe if Planet 9 is real, then that maybe solves that problem because it's sort of in that mass range. Do you think that's still a problem that our solar system seems to not have that? Sort of just, seeing a sort of mini Neptune sort of somewhere or super Earth somewhere within sort of the regular architecture. Assuming, Planet 9 seems pretty far out, but is that still weird, or do you think there's something about in these dynamical models or pebble accretion models that sort of can get around the solar system seeming weird compared to the planetary systems we know about these days?
So, all right, so this is a very good question. I often give talks where I talk about this kind of thing. So the solar system is not that weird in not having the super Earths. The statistics are still not that good in terms of the exact fraction of main sequence stars that have them, but it's ballpark a quarter to a half do. So the fact that our solar system doesn't means that we're in, at least a 50-50 shot. Maybe we're in the majority, or at least it's a 50-50 shot. So it's not that weird. Although, of course, we want to know why. Then, even if it's not that weird, what is it that causes some systems, a large number of them, to end up with super Earths, and we didn't? And so one idea that's been thrown out there is that it's Jupiter. So in the context, if super Earths form from migration, if they kind of migrate in cohorts and end up close to the star, then one gas giant that's blocking their path might hold them back. So maybe Jupiter formed fast enough to hold back, a bunch of icy stuff that instead became Saturn and Uranus and Neptune. And that's a kind of a nice idea. And it could plausibly work at the solar system level. It can't work at the system level, at the global level, because there's not enough gas giants out there. And so we know the statistics of gas giants is such that maybe 10%-ish of sun-like stars have gas giants, but then what fraction of stars don't have super Earths? At least half. And so there's not enough for it always to be gas giants. And so it might be something else. It could be something related to the isotopic dichotomy of the solar system, something that's chopping planetary systems in pieces, either the growth of cores that block the flux of pebbles inward to prevent inner stuff from growing really fast and becoming super Earths, or maybe it's a lot of ring divisions from pressure bumps within, within disks that prevent inner stuff from grabbing onto pebbles and growing and becoming super Earths really quickly. So I would guess that it's something related to those, but it's really not well nailed down. And so going forward, I think future studies that try to correlate different aspects of planetary systems, like one key thing is correlations between super Earths and outer gas giants, whether there is a correlation or an anti-correlation or whatnot. Those kinds of things can help constrain those ideas. Sorry, that was a long answer.
But an interesting one. Celia, you're muted.
Sorry. Yeah, thanks. Do you have any other questions, or I can just ask one of the questions from the audience here?
Let's go to the audience.
Okay.
Yeah, sure.
So the first one we received was, how likely is it to get a double planet Earth-Moon. So I guess it's all likely to form an Earth-Moon system, if I understand the question right.
So we think that, I mean, the context of the question, we think that our moon formed, in the last giant impact. That's kind of the prevailing idea now, that Earth formed from a series of impacts of these kind of planetary embryos that were roughly Mars mass or so in the inner solar system. And so in the context of our solar system, you might wonder, if you form the Earth 10 times, what's the likelihood of ending up with a moon? And that depends on the details of the last 1 or 2 impacts. And I don't know the exact numbers. I think it's pretty high, but there's studies by people like Robin Canup and others who have looked at the details of what types of impacts, giant impacts, really are required to produce the moon. There's been less work to look at the less constrained problem of, if you form the Earth 10 times, what are the odds of getting the moon? But there's numbers out there somewhere.
Thanks. So the next one is, what about the role of planet 9 or 10 in the formation of the solar system, even if we didn't discover it yet? So is it considered in those simulations in the different model?
So I can talk about it formation. I don't know if Meg, you want to add anything afterwards.
Yeah, that sounds good.
So Planet 9, right? What its existence is still uncertain. Right? I think it's an awesome idea. Whether or not it exists remains to be really determined. If it does exist, where could it have come from? An object that's 5-ish, if I think 5-ish Earth masses on an eccentric orbit that's hundreds of AU in size. That'd be really disconnected from the solar system. So how would you get it there? And there's been a few different ideas thrown out. I think there's 2 that are plausible, personally. So one of them is capture from another star. So if another star had kind of a system of ice giants and was in the process of, those ice giants had gone unstable and were in the process of having an instability, one of them could be on a very eccentric orbit that's wide enough to be captured if the sun came within a couple hundred AU. And it can, in some cases, be captured on an orbit that's kind of Planet 9-esque. And people who have done the numbers on this find that the most optimistic numbers are maybe 1% likelihood, probably much less, during the cluster phase when the sun was still in this cluster. The other model for it that I think is more plausible is that it would be a leftover from the formation of the ice giants. And so the ice giants, there's only one model has ever succeeded in kind of matching the ice giants' properties, a formation model. And the idea of that model is kind of similar to the super Earth formation model I was talking about. So the idea being that Jupiter formed first, we think, and Saturn got big, and then those 2 were either migrating inward and outward or just kind of more or less camped out in one spot. And a bunch of outer stuff, migrated inward and got blocked by this barrier of Jupiter and Saturn. And then what happened then is they bashed into each other and grew into the ice giants. And that model can reproduce the ice giants quite nicely. And sometimes there's an extra one left over to be ejected during the instability. But the process is not 100% efficient. For every Earth mass that ends up in the ice giants, about 1 Earth mass of stuff is ejected. And so there's several objects that are kind of Planet 9 mass that would be ejected. And so if you consider the solar system in isolation, they'd be ejected and never come back. But at this time, the sun was probably in a cluster of stars. And so if it got kicked out, and before it got completely kicked out, gone, it was kicked from the other end by a passing star. It can be trapped on a Planet 9 orbit. And the best case scenario for that is like a 5 or 10% thing. So it's not that implausible. Sorry, I guess I said a lot again. Sorry, do you want to add anything, Meg, about stuff?
Yeah, I mean, and there's interesting things. I think it's whatever 500 million years or something. Mega years is something that, I mean, you look, the lifetimes of embedded clusters is pretty short. That again, you have to get the timing. Everything's got to be right, which adds even more sort of to these timelines of like, you start getting to very small percentages, right? Means that everything, and so that's the other thing too, is a lot of to keep the Oort cloud, you need to be out of the cluster, which means that, because we think that's been placed by, Nielsen migration. So the gas has to be gone at that point. So to have that giant planet, saved, right, means that still the full reorganization has to happen later because you have to be out of the cluster. Otherwise, we wouldn't have the Oort cloud. Stars coming in would have obliterated it. And so I think for observers, we still have this uncomfortableness of like, how do you get this thing out there? There's maybe a way to do it, but does it start getting to so low probabilities? And the other thing I keep wondering about is that Neptune would have kept migrating. You sort of have to have it dip in the density to sort of stop it around 30 AU. And so it kind of makes sense what we see now with the cold classical. We've kind of waffled back and forth of they formed in situ or were moved out. I mean, I think we're pretty, solid on it wasn't that they were in place as part of the hot population. They really were formed in situ. So maybe that is enough to get you that dip in density. But then to sort of come back around and have a larger planet afterwards, you kind of wonder, why was it that there's a dip in the density there? But we don't necessarily, why is it there? But we didn't, that change from the rest of the small bodies that were scattered by Neptune and Uranus and Saturn and Jupiter. So for me, I still have this uncomfortableness of like, why that part change, how does that story or that puzzle piece fit in if Planet 9 is real? So I think it has some interesting challenges, I think, to formation models, or at least really getting into the very details. I think the other thing about Planet 9 is that we should not see its signature on the Kuiper Belt. And so there's been some recent papers by Sam Leller and others that have looked at what is the impact on the Kuiper Belt. And very significant impact on the scattered disk shouldn't be there. And so the original proposed orbit for Planet 9 actually had that problem that it would have created structure we would have seen in the Kuiper Belt scattered disk population. Now, obviously, this is degenerate. There's a lot of parameters in an orbit that can be changed in the mass. And so the revised estimate from Brown and Bagatine doesn't seem to have this problem. So right now, basically, there's no other signature other than these very, very distant objects that I like to call the inner Oort cloud, because they seem to be sort of so isolated from Neptune that really the only signature could be Planet 9 or some other potential mechanism that's causing this orbital alignment that we're seeing, where they're all coming to perihelion at similar locations. I think there's a lot of evidence that suggests that Planet 9 is real, but I also think that there's some evidence that suggests that maybe there are biases there. And I think the interesting thing is that this LSST survey will hopefully find more objects and be a uniform survey to answer that question, as well as other groups like Chad Trujillo and Scott Shepard and Mike Brown and Constantine Bagatine that are also doing searches right now to try to find Planet 9 and find more objects in this sort of no man's land that shouldn't be influenced by the giant planets that would show the orbital alignment indicating Planet 9. So I think there's still more to do. I think there's some still debate in the community. I think there are groups on both sides. I think some are more adamant than others, but I think it's an interesting theory that I think we can test. And so that's what people are doing. So it's the beauty of, I think, it's a question for planet formation. It's also a thing on observations. And so we're, I think, all trying to get more data to really answer that question of whether it's there and how did it get there.
Thanks. One thing I was wondering is how many of those inner Oort cloud objects are we expecting to find with the LSST? Do you have an idea of the number?
Not a good number, because it hasn't, I think, been fully put through the survey simulator. But it's 40,000 Kuiper objects. So ballpark, I bet it's something, and it's at least a few, maybe tens, maybe more, maybe hundreds. We'll see, because they're all in the northern hemisphere, and maybe they are only located there. And so we won't find any in the south, because they'll all be coming to perihelion, sort of where the proposed Planet 9 is. So maybe there'll be less objects than that. But I think it'll help answer the question, and also other surveys might get there sooner. So the interesting thing is, Planet 9 should be detectable in LSST. So it should be visible. And one of the tricky bits is it could be hiding in the galactic plane. So in one of my plots, you notice there's like sort of structure within the Kuiper Belt, and just showing the different objects. There's like a small patch where nobody looks, because it's in the galactic plane where the star densities are high. And so it becomes a challenge where you actually have to do image subtraction to even see the moving objects. So a lot of us just avoid it, because we can go do our science without making it really hard on us. So the New Horizons team had to deal with this challenge to find Arrokoth to go to after the Pluto encounter. So LSST is designed to deal with that. And so although groups that are looking for Planet 9 are trying to deal with that, I think LSST will be able to really search that region. And so if we don't see Planet 9 the next few years through the surveys that are already operating, and LSST, I'd start wondering why we can't see it. And does that mean its properties are different? And that might sort of add more to the story, whether we believe it's real, or is it telling us something about its properties that make it not like the other planets?
Great, thanks, Will. So question here for both of you. So what future of observation tests do you think would be the most important to address the key question about planet formation?
That's a good one. I guess I started talking, so now I'm stuck. I have to answer it. I mean, there's a lot of interesting things, and so in terms of a lot of this, the ideas that I was talking about in terms of solar system formation models have come from, you know, they have their origins in people thinking about explaining exoplanet systems, and so I think a lot of them will be testable with correlations between populations of exoplanets, this kind of things. Like when we get better information about the compositions of exoplanets from more reliable bulk densities and things like this, and correlations between the inner and outer parts of systems, which will happen when you get surveys that are going to be able to probe the, you know, the outer parts of planetary systems, this kind of thing. I also am a big fan of the interstellar objects. I think they're so cool. And they're like pieces of exoplanets. I often give talks on solar system and exoplanets in the same talk. And then I like to end up with the interstellar objects, because then it's like we have one of those guys from from another system, not that system, is flying through our system right now, and we can say something about it. So yeah, that's all I got. I mean, I wish I could be more specific and be like, go look at this little part of the sky. If you see a thing move, that means I'm wrong, but you're not going to see it, so I'm right. You know, this kind of thing. But I don't have anything quite that specific, unfortunately. Sorry, Meg, do you have stuff?
I think it's numbers. I think, I think every leap has been large number of objects, I think, or we're probing in different ways. So like dwarf planets gave us a lot of picture of oligarchic growth in some scale, because they're very different from the very small Kuiper belt objects. So a lot of it is getting observations and getting, larger and larger numbers and data points. But also a lot of it's been a surprise. So, I mean, Sedna is not Sedna, and where the objects that might be, interacting with Planet 9 are not supposed to be there. So when they were found, right, I think there's a lot of observation starts to get you into those questions of why is that there? And I think that serendipity will increase. But also it's getting into the very details of that, putting in that puzzle. I think we've got a lot of the broad sweeps of it, right? But really putting in those very small pieces in the center, I think we're still figuring that out. So why Kuiper objects are there certain colors they are, how that actually goes back to the original planetesimal disk. That's what my graduate student Laura Buchanan's working on, trying to take dynamical models, paint the objects, and then watch and see how on the survey we're doing Colossus, to get those colors to see where they are. Actually going and seeing, are there cold classical objects contaminating the hot population? We're still figuring that out and what that might mean. Are they hiding in resonances? So does that tell you that they're really detailed of how Neptune sort of stopped its migration and how it jumped at the end in some major axis? And so I think there's a lot of detail that'll be there, but also the unexpected. And so I think for me, we're going to see a lot come out of LSST, because we're, 5 million asteroids, you're going to see something that's interesting. And we're going to get, not only are we going to detect them, we're getting colors of them brought in multiple filters. So it's a proxy for composition, and same thing for the Kuiper belt. I don't know how to plot 40,000 objects, but I already know we did a lot with 40,000, with 4,000. So when I get to 40,000, what things are going to pop up there? So I think there's going to be a lot of questions and a lot of sort of taking the broad strokes we have and looking at it in this finer detail and seeing if it holds up. Just like the broad NICE model works, but we've had to tweak it and change it, right, to explain the observations as we go, right, because we're now getting much better detail. So for me, it's getting the Rubin Observatory and LSST online. And so, we're expecting science operations end of 2022, beginning of 2023. So I think it's not that far away now. I think that's gonna be the data set that I think we're gonna be working on for decades, really pulling through.
That's cool. That made me think of one thing I was just gonna say real quick, is that an interesting kind of philosophical point that comes up is people often wonder why models like the Grand TAC or these other models are so specific. And so one interesting thing about it is just that we have so much data for the solar system and so many constraints that a very vague, simple model can't work. And so you have to get in the details. And so it's really fun trying to, model the solar system in that sense, because there's a lot of constraints and there's a lot of ways for ideas to be shot down. Whereas for exoplanet systems, until recently, I mean, this is changing all the time, there were fewer constraints. And so it was easier to just kind of throw out very vague models that could explain the general tendencies that we're seeing without having to get in the details. And now that's changing because we're getting more and more demographics, but it's still this in the sense of trying to match a population rather than to match an individual, which is, it's just interesting from a philosophical point of view. I'll shut up now.
So we're like, it's almost 6:30 here, so I'll try to ask a few more questions quickly. Here, whether the environment in which the solar system formed could have played an important role in the shaping of the solar system. I think it's more addressed to you, Sean.
Sure, for sure. And so I've seen some studies, I don't know if they're new ones, as of several years ago, the last time I saw this, studies that were trying to constrain the density and the number of stars that within the sun's birth cluster. And so what are the constraints on that? There are constraints saying that stars weren't so close together that other stars came within 10 AU and destroyed this, where the other planets are. At the same time, there were enough stars there that there were certain radiogenic elements that we measure in meteorites, the most famous of which I think is aluminum-26, that's produced in massive star winds and supernovae that ended up in our sun's planet-forming disk and is responsible for Earth having its current water content in a lot of different ways. And so using those constraints, the birth cluster of the sun was probably 1,000-ish stars, something like that. And simulations of clusters of that size range find that the typical distance between stars, the closest distance between any two stars during the evolution of the cluster, which lasts maybe 10 or 100 million years typically, is something like hundreds of AU. And so you can imagine, well, if another star passed by within a few hundred AU, what would that do to the solar system? And in general, it wouldn't disrupt the orbits of the planets, but there may be a signature of it in the outer parts of the solar system, in the Kuiper belt and such. And there have been ideas thrown out there that part of the orbital distribution of objects further out there have been sculpted by that. And so there may be a signature of this in the distribution of outer solar system objects. And in more extreme cases, it could on other solar systems, it could have a bigger effect. Do you want to add anything to that, Megan?
Yeah, I mean, I think it's an interesting thing to try to think about the early conditions. So my PhD thesis, I was looking at, how the one object we had at that point in this inner Oort cloud region, how that might constrain an embedded cluster model or scenario, like what the cluster might have looked like. And one of the things is we can't even figure out which stars were part of the sun's cluster. Like compositionally, it's because of things being moved around the galaxy, we can't go, these stars were all together with the sun. And so some things we'll never be able to fully go back to, I think, in some observational ways. You think it'd be easy to be able to take spectra and be like, oh, cool, these are all similar composition stars. They must have formed in the same place, and it's not necessarily true. So it's sad to think that in one way we can't tell necessarily where all the siblings for the sun are to get a better sense of what that cluster environment looks like. But I think you're right, there's clearly signatures within maybe the solar system that in other populations it's been erased, that history, right? The inner solar system doesn't know about what happened in the outer solar system, but maybe it is true that where the edge of the Kuiper belt is and where the Oort cloud is and this maybe inner Oort cloud region are telling you about the stars. And the example being, like, we know the Oort cloud's there, so it had been placed after this process because it might not have been there. And so I think it's interesting to see the combination of all these things, or knowing that there had to be a supernova sometime nearby, because that's why we have aluminum-26 and all these other radioactive elements enriched, right? It had to come from somewhere. And so yeah, I think, and I think we can think about what things might there be, but I feel like there's always getting more observations will come up with unexpected things that'll shed light on these areas that we can't even predict today, which is, I think, the fun part of observations. Things that we might not have thought about, right? thinking that there might even be a ninth planet. Or well, another ice giant sitting up further away is not something even 10 years ago was necessarily on the radar for the field.
Okay, excellent. And what might maybe be the last questions, because we're nearing the end of the time for this. So I'm grouping two questions in one for this. So about the three models that you presented, Sean, there, is there do you have a favorite one, or is there in general a favorite one when choosing between those three? And what would be the ground for that? And related to that, is there one of these models that best reproduces the Trojan population?
All right, so right now, if you had to ask a group of planetary scientists or astronomers, they would all say the Grand Tack. And the reason for that is just that it's been around the longest. And when it first came out, I spent like a year or two giving talks about the problem beforehand because we already had the solution coming to try to motivate the whole thing. And so that one has become like the most known, and the paper is cited a lot of times and so on. And the other two models I think are kind of struggling to become recognized because they work just as well. And so when I talk to people who do observations of disks around young stars, they think that the Grand Tack and early instability models are kind of ridiculous. And of course, it's these rings. They see rings everywhere in ALMA data. Why would we even be thinking about migration? You don't need that. And when you talk to dynamic people who are more into dynamics, they really like the early instability model, because if the instability of the giant planets can already explain a lot of things in the outer solar system, then just by shifting the timing compared to previous incarnations, all of a sudden it can explain the inner solar system at the same time. That's pretty nice, right? And so there's all these kind of, but those are just mind games. And so we don't know what happened. So the real game in moving forward is trying to falsify as many as possible, because it could be none of them, right? It's not like we should bank on any of them. And the goal is that they're ideas that are useful for advancing what we think and our understanding, hopefully. But they should not be taken as things to believe or think that one of them has to be right or anything. They're just kind of useful tools to hopefully go and understand the next thing. And in terms of the Trojan population, sorry, the Trojan population has been shown to be reproduced really nicely by the instability itself. And so each of those models for the formation of the inner solar system is compatible with a giant planet instability. In one model, it's the kind of the central part, and the other ones, it would have happened after the kind of key dynamics. And so the instability in the giant planets naturally basically captures outer solar system objects on Trojan orbits of Jupiter that have this broad inclination distribution like the observed one. And so none of the three models is really constrained by that. Does that make sense?
Excellent. Well, we might have time for one quick last question. Coming back to Borisov, because everybody is very enthusiastic about the interstellar comets. So 2I Borisov is similar to our own solar system comets, at least in some sense. Does that mean that the whole system of 2I is similar to our solar system in terms of the giant planet architecture?
Oh. I think as an observer, I would say that's reading way too much into it. It's 2 data points, and effectively one that's actually like really common. So, or had a tail, Oumuamua also had evidence of non-gravitational effects because we see we see its orbit change in position. So we think it outgassed a little bit too. I think, it's hard to read that much into it. It's 1 planetesimal or 2, right, that we've sampled. So can we really understand much about where its location was, other than we can understand sort of its composition in broad strokes of what that means compared to our solar system? But when we look at our own comets, we can't even pinpoint where it came from in our own solar system. We have a theory of how we go from long period to short period comets, but even then, like, the sizes don't quite work. Kuiper objects are still quite much larger than cometary nuclei, and so what is happening as they come in from short period comets? So even within our own solar system, we still can't pinpoint exactly where different comets of different compositions come from. So I think it's going to be a challenge to do that in a solar system we can't even see that fine detail of. But I'll let Sean sort of touch on the interesting sort of dynamic parts of that.
I would say agree with what you said. In general, if a planetesimal formed around another star and ended up in interstellar space so that it could come through the solar system, we know that it had to have the conditions to get out of its solar system. So, you know, that means it may have been because of giant planets like ours. It may have been because of giant planets that are different than ours. You know, Jupiter can eject a bunch of stuff from the solar system. A hot Jupiter can't, because it's too deep in the gravitational well of its star. And so you can constrain this using simple math about what types of giant planets can eject stuff and which ones can't. And so, you know, you can put very simple constraints on what the giant planets must have been like if it was planets that even did the ejecting. Maybe it was a passing star that did it or something else. So it's still, you can't really constrain things as much as you'd like.
Yeah, and I think it's worth noting that at least for our solar system, that whole process was messy. So, I mean, in some sense, it might be reassuring that, you know, we aren't the only interstellar polluters, and that, you know, we know that a lot of material was kicked out. Neptune's pretty good at keeping things in the Kuiper belt and into the Oort cloud, but Jupiter just knocks things out, right? It hits home runs way out of the stadium. So maybe there's some reassurance that if it is have something to do with giant planet migration or even just gravitational scattering, that, you know, we're not the only one that's been polluting interstellar space, and that maybe that's why we're seeing these as a frequent occurrence.
Well, I guess we're out of time, but I want to thank you both again. It was really great talks and great chat afterwards. So thanks a lot for that. And thank you everybody who watched the duologue, who participated, asked questions. It was really great being here with all of you today. So
thanks for inviting us. It was fun.
Yeah, indeed.
Sorry
to jump in, I also wanted to myself, on behalf of ESO and Henri, all the organizers, I want to thank the speakers and thanks Riel, of course, also for chairing the session. Very, very, very interesting duologue. Thank you very much. A lot of food for thought and also perspective. So really, really thank you very much. And just to remember people that the video will stay on the channel, so you will be able to see it again and again, and we also post it on our web pages, the link on our web pages, and also about the questions. So we are collecting all the questions, and we will give the question to the speaker, and then we will provide some writing answer also on our web pages. So no question is going to be Okay, but thank you again for being with us. Thank you everyone for participating and attending our event, and see you next time. Thank you again. Bye bye.